This is the first lecture that the Society has organised in memory of one of our greatest servants, Vic Barnett, who, apart from all his academic achievements, did all manner of honorary duties within the Royal Statistical Society, and indeed one of his many projects that he pushed through with great and characteristic vigour was us buying this building about 20 years ago, I think now. It was when I was certainly an honorary secretary and Vic was the treasurer, and although a lot of people contributed, it was Vic who drove the project, and that was Vic all over. I mean, when I first met him, he was a reader in statistics at Newcastle. I was a new lecturer, and there was this kind of whirlwind going around the department. And then he moved on, and I stayed at Newcastle. And then about maybe 10 or 15 years later, he breezed up to me at a conference and announced that the future lay in environmental statistics. And he invented something called SPRUCE, which was Statistics for Public Resource Utilities and Care for the Environment. And so that was Vic in his green phase. And indeed, I think, if not the first, but one of my early meetings with John was at the first SPRUCE conference that Vic organised. When we were given the opportunity through basically a very generous decision by the SPRUCE charity that Vic founded to use the residual funds after Vic's untimely death to hold a lecture in his honour, we absorbed it into our honours system. We have a whole series of medals honouring different aspects of statistics, and for the first time we had an award in environmental statistics. And amongst some very, very strong nominations we got for the first award, Jonathan Tawn, my friend and colleague at Lancaster, was deemed by the committee, which I may have chaired, but I was certainly not allowed to influence the result, was awarded the first Barnett Lectureship. And so it's a great pleasure. John, I suspect, is known at least as well to many of you as he is to me for his work in environmental statistics, and in particular things to do with the natural environment and extremes of weather and so on and so forth. Really all I have to do apart from that is just invite John to give the first Barnett lecture. John Tawn.
Thanks, Peter. I'll give you about 10 later. Okay. It's a real pleasure to be able to present this talk today. Vic was a colleague of mine at Sheffield, and he had two red papers for the Society, which actually very closely tie into the things I'm doing today, so you could view the work that we've done in subsequent years really as sort of a natural evolution of the work that he set out. So in particular was a paper on multivariate ordering, considering all the different aspects about, how do you think about what an extreme is once you go outside one dimension, and a lot of the sort of multivariate methods that I present today sort of build very naturally in a way on from the sort of the framework that he set out for thinking about that. He also had a paper with Toby Lewis about looking at extremes to do with risk of diesel freezing, and in particular there it was looking at the time series aspects of very cold behaviours. And again, I'm going to look at almost the converse of that, looking at heat waves today, that essentially sort of the style of modelling is set out in Vic's early red paper in the 60s on that. So it's sort of difficult trying to think of what to present at an event like this, and so what I've tried to do is pick out some of the applications that I've enjoyed working on most over the years, and try to put a story around those which sort of hopefully pulls those together, so you can see the theme of connectedness in the research, which I'm sure wasn't there as we actually did the research, but hopefully with retrospect we can see there really was some logic to what we were trying to do in the developments. So I'm going to sort of look at three sort of key areas of applications I've worked on over the years. So flooding, I'm going to look at two aspects of that, one to do with coastal flooding and one to do with insurance aspects to do with river flooding. Offshore safety, recently I've been doing a lot of work with Shell to do with offshore oil rigs, but I'm going to present here things to do with shipping safety. And then more recent work I've been doing with Hugo, who's pleased to see here today, on heat waves. So let's just start sort of back to the basics of where sort of extremes arrive in many environmental risk assessment problems. Suppose we're trying to look at a nuclear power station, and such as the one that EDF are about to build. And then we need to know about what's the risk of flooding, or trying to control that risk of flooding at the power station from the sea level. So they might specify a certain level of risk that they want, and a natural thing to do is to think over a certain time period, what's the probability that they want for flooding to occur or not to occur over that period. So just to illustrate that here, let's just think over a 10-year period not to flood with probability 0.9, which isn't that safe really, but you can see that's a starting point, which actually means that in each year we want the probability of flooding to be just 0.1. 0.01, something like that anyway. So flooding basically to occur once on, if everything was stationary, flooding to occur once on average every 100 years. And you see, that isn't that safe, so really in more realistic situations, they want to be looking at the 100-year, once in 1,000 year, once in 10,000 year level events. So here's some sort of pseudo data just to illustrate the decision making and the philosophy behind an extreme value approach. Is that typically we want to look at a level which is, say, once in a 100-year level, but we've only got a much shorter series of data, say 20 years of data. And so if we're asked to, is that level high enough to give us a level of protection, it's very difficult to say. We can't just look at the past data to give us anything there, because we can see, naturally we would be very unlikely to have seen any exceedances at that level. So what could we do? One thing we could do is just wait and not design our seawalls for another 500 years till we've got a lot more data. And after 500 years of data, we might have got something like this. We might have seen something like 7 exceedances over our 500 years, and seeing that level might be quite decent, but of course, that's, we can't wait that long. In particular, we can't just sort of wait and see or just even guess these levels, even though they're beyond the range of the data, because the spend that's involved on coastal flood defence is massive. Just over the last 10 years, £1 billion spent on coastal flood defence in the UK. And if we get that spend wrong in the way that investment goes, so we build the seawalls too high, if we built it a metre too high, just on a 100-metre length of seawall, it's £150,000 of wasted money. So we need to get the height of it right. Clearly, if we get it too low, we're going to incur floods that we really don't want to occur as well. So we really need to estimate that level quite well, even though it's beyond the range of the data and we haven't got anything very easy to get a tangible handle on that. So one thing we could do is we could fit statistical models to our data. So here's 2 examples we might have tried to fit to our data, and they both look in the range of the data, they both look like they fit quite well, but each of them has got, by order of about a factor of 100, quite different probabilities of the probability to exceed this really high level. So we can't really say that's a very reliable way of going forward to do the estimation. So the complication is that we can change quite dramatically what's going down in the bulk of the data without it necessarily changing the tails. And so therefore we need to have a strategy that's more focused on the tails rather than trying to model the full distribution. So that within extreme values, the sort of natural approach to do this is to focus on a maxima over a sample. And so the traditional approach is to block the data, our 20 years, into 20 individual yearly sequences, and then inside each sequence pick out the maximum from the year, giving us 20 values overall. And then just look at modelling the distribution of the annual maximum. Now, which distribution should we use for the distribution of the annual maximum and to try to estimate the probability of exceeding this high level? Okay, so just to try to see the logic behind that, suppose we start off with 2 quite different distributions for what the original sea levels would like, and we looked at what the distribution of the maximum over the year would be. So this would be what the maximum after over 10 observations is for those 2 distributions, if I simply just relocate and scale the distributions so they basically agree. So you can see, even though we start off with quite different distributions, by the time we start to take maximum of 10 or 100 or a whole year's worth of observations, the difference between those 2 distributions is basically negligible. So what this suggests is that whatever we start off with the original distribution for sea levels, by the time we focus on the maxima, we've narrowed it down to, in this case, a single family of distributions to worry about. So that's going to give us a much stronger basis to look at and extrapolate, rather than just to try to fit to the observations that we've got in hand. We've got some sort of theory now which says, okay, if we focus on maxima, we can narrow down our interest to a smaller set of distributions, not the whole set of distributions, but to a smaller set of distributions. And that will give us a much more rigorous statistical basis for doing the extrapolation. So the distribution that these things collapse to, once we focus on maxima, is this distribution known as the generalized extreme value distribution. It's a 3-parameter distribution with a location parameter, a scale parameter, and a much more subtle shape parameter that determines effectively the heaviness of the tail of the distribution. So we can see that by focusing on maxima, instead of putting any distribution, we can now only need to potentially, at least as a starting point, look at this distribution and see how well this fits the data. So we could take our maxima data, fit the GEV, and above our level we might see that over 100 years we might expect, under that model, that there's 1.6 exceedances over 100 years, so it's going to be roughly around the 100-year level, which is what we might want. And we, of course, can put confidence intervals and everything on that as well. So that's the basic strategy of extreme values, is to say, okay, the full distribution is complicated, but maybe by focusing on the extremal features, there's a simplification that arises, and I can use that simplification to sort of suggest a form that I can use to do extrapolation to much rarer events. Of course, it's not just as simple as that. If we look at maxima, we realise that potentially when working with maxima, we might be inefficient in our use of data. We collect all this data and just use the biggest from each year. There might be some years with multiple big values in, and some years with no big values in. So a more natural approach instead is to model the exceedances above some high threshold level, and therefore we're modelling these excess points here instead. And usually that leads us to have more observations to model the extremes from, and we can do the inference of these extreme value parameters a lot better. And in that case, the appropriate distribution it comes in this following way. So we'll take our original variable, like the sea level variable. It's got an upper end point of this, and it turns out that if we look at the excesses of threshold level U, the excess amount above that threshold scaled appropriately. And if we look at the distribution of this, if this converges to something that's non-degenerate, then the only form that non-degenerate limit distribution can take is this distribution over here, which comes from is the generalized Pareto distribution. So this is the equivalent theorem for threshold exceedances that parallels the result for the maximum of variables which gave the GEV. It's no coincidence that we've got a shape parameter here that looks like the shape parameter I had in the previous distribution. They are exactly the same parameter. So the beauty of this is I can learn about this parameter that was determining the tail behavior of the maxima. I can learn about this from more observations in the extremes. Now, that's a limit distribution. The way we apply that in practice is we unwrap the conditioning and assume that this holds above some high threshold level. So in the end, that gives us a sort of a tail of the distribution function having a particular form driven by this generalized Pareto distribution. So that's the philosophy behind extremes, is that we use an asymptotic theory to narrow down out of a full set of distributions onto a particular subset of distributions, which we can either use for the maxima or for threshold exceedances, and then we can use that in applications. So I'm going to talk to you now about a couple of univariate applications that we've looked at. So this goes back to the work I guess I did originally in my PhD thesis and just beyond that. So if you're interested in the extreme sea levels, the feature I haven't mentioned, which is very important, is that the sea levels aren't quite as simple as a nice IID series. They've got a lot of structure to them. In particular, the sea levels basically made up of the tide, which is the completely deterministic component of the sea levels movement, so it's completely driven by the movement of planets, and the surge, which is the meteorologically induced component of the sea levels. Now, this is the sea level after we've averaged out surface waves, and lots of the research we've done also deals with surface waves, but I'm not going to cover that today. Now, the surge is much more like a stochastic variable that we are much more as statisticians used to modelling. Now, the complications, we can't then apply our extreme value methods directly to the sea level variable, because the key source of the variation in the sea level variable is the deterministic movement of the tide, which is the dominant variation form in the sea level. At many places you go around the coast, you'll see that the tide will be responsible over a day for the variation of about 5 to 6 metres, whereas the surge or variation over a day might be responsible for about a metre change. So much less important in terms of the basic variation over a daily scale. So the idea within the way we approach this problem is to separate the sea level into a tidal and surge component. And then we can treat the surge as a stochastic variable which we can model its extremes by using the extreme value top techniques I've just set out. And then the idea with that is that we then can model the tail of that, we can then combine back the tide and derive the distribution of the sea level variable. Now that sounds beautiful at first, but the complication is there's lots of physics going on in the surge variable, and that the surge is very much influenced by the state of the tide, because surge is just a bulge of water that's moving along, being pushed by the weather along the coastline, and at high tides there's less friction with the bottom of the sea, so that bulge of water moves at a different speed than at low tides. And a consequence of that is that the tides it looks like there's obvious dependence between tides and surges, with the biggest surges typically occurring on the rising tides in shallow water areas. Now, as one approach is then just to model the extreme surges with a covariate, which is the tide, or a more subtle approach is to use something called the Skew Surge approach, which I'll illustrate on the next slide. But in both cases, the idea is we look at the extremes of the surge, put the tides back in, and then we can derive the distribution of the sea level. So this is where I think collaborating with non-statisticians helps tease out a lot more of the structure of the problem. So in our initial analyses, we just looked at the surge, which is, so the blue here is the tide, the black is this overall sea level, and the red is the surge. And you can see here on this diagram, the peak surge is occurring on the rising tide. But to try to take out that interaction effect, if instead we worked with something called, the oceanographers call the skew surge, which is the difference between the peak tide and the peak sea level, even though they don't necessarily occur at the same time, turns out that that variable doesn't suffer from this interaction effect to water depth. And if you look at the joint distribution of those, they appear very nicely unrelated to each other. So it's much, much easier to model the extreme skew surge and combine it back together with the distributions of high tides to derive the sea level extremes. So we've done that, and you can. The beauty of when you do that is that the surge extremes change very, very smoothly around the coast. So it's very easy to use smoothing methods and statistics to sort of exploit and share information from site to site about what these skew surge extreme value parameters are. Whereas the tides are predictable and they vary in a complicated way. You picture a tide coming down an estuary, it blows up the sea level variation dramatically. And those you can model and find out and map using sort of much more advanced numerical model techniques. So just to give a really quick feel for what happens here, this is what the 1 year sea level return period looks like around the coast. So it's always difficult to plot these things, but here we start up at Wick near the top of northeast Scotland, and come down to Immingham, down to Lowestoft, and then round to London, to Dover, along the south coast, into the Severn Estuary, out of the Severn Estuary, round to Wales, round to Morecambe Bay, and then up into Scotland here as we go around, all the way around the UK coastline. And all the variations there that we can see, which are varying over about a 4 to 5 metre range, from place to place, they're all to the same datum. All that variation is really being driven by the variations in the tides from place to place. If we look at the difference, though, between the 1,000-year return level and the 1 year return level, we end up with something that varies much, much smoother over much smaller variation across the country, typically varying by about a metre from place to place. And this is really capturing the skew surge tail, and it's taken out the effect of the tides. And we can see that as we come down the east coast, the surges gradually amplify in size as they get forced and narrowed in basically there. And whereas if you come into the Severn Estuary over here, that doesn't happen because that skew surge is pushing the very extreme things on the rising tide, but not necessarily on the peak tide. So there's a lot of sort of structure that comes through, and you can see in these plots. And these end up the basis that are now used for all the decision making about coastal flooding and how high the sea levels should be at different places. Moving on to a second topic, here I worked on the sinking of the Derbyshire, which was reported back to the Society a number of years ago. But I think this is an interesting study, so let me just recap on this. So the MV Derbyshire is the largest UK ship that's been lost to sinking. Largest in terms of size, not obviously in terms of numbers of people. So there were 44 people on board when it sunk during a typhoon. But to give you a sense of the scale, it's about a 6-lane motorway wide and about 2 football pitches long. And when it was lost, there was no mayday, so we had no sense of what caused the sinking originally, but eventually the wreckage was found and photographed, and then there was a High Court investigation to try to understand the story of what had happened. Essentially, early on in the investigation, from the photographs, what they thought had happened was that this hold here, the cover for this was broken by severe waves, and that led to flooding inside there, and then that meant the ship sat lower in the water, made it easier for then a subsequent wave to hit this part and make that then come off and fill with water and so on all the way down this process. And basically what they realised through their studies that once this first hold cover went, it was effectively a guaranteed process that the other hold covers would go all the way down the ship until it sunk. And the process from that first hold cover coming off and starting to fill with water to the ship sinking was about 3 or 4 minutes. So, there wasn't a lot they could do in that process once things happened. What the court were interested in was how much, if this was the process, then basically, how important was flooding that might have occurred in the front end of a ship prior to this first hold for coming off, which would then influence the fact that the ship was sitting lower in the water. So the design standards for its front hold cover was 42 kilopascals. So the basic question the court was interested in really was what's the probability of getting wave impacts of greater than this critical level, depending on how the ship was run, and that obviously involves what type of damages might have occurred earlier in the storm. So the information we had in this case was we had hindcast wave data from the typhoon, and we also had a massive number of wave tank studies run in different wave conditions, looking at, you can see the wave tank ship here, measuring the impacts of the waves on this front hold cover in these different scenarios. And then the people I was working with on this, they also had constructed some very helpful covariates which summarise the characteristics of the wave conditions in each of the wave tank scenarios, describing the main features of the waves which would be important for looking at impacts on this cover. So the approach we took then was to look over the storm at how the distribution or the probability in some sense of getting a critical wave impact varied with the conditions through the storm hour by hour, and could combine that together to look at what was the probability that the ship sunk under the different scenarios. So before I got involved in the investigation, the courts and the people working on it had tried some statistical approaches. So they'd tried something called distribution 1 here, which was just basically a wider distribution for the wave impacts. And they'd looked over a whole range of these conditions that they were interested in, as to whether the waves were as predicted or bigger, and whether the ship hadn't got damaged or had some early stages of damage. And basically, whichever of those it was, it turned out pretty likely that the ship would have sunk, so the probability of sinking was high. But then halfway through the investigation, they tried a different distribution they thought was appropriate, and then basically they found whatever the different condition, it was unlikely that the ship would have sunk. And so the ability to discriminate between these different scenarios that they were really interested in was obviously being swamped by the statistical uncertainty in their modelling. So as soon as we were told about this problem, the natural thing for us to think about was that the extreme wave impacts would be fitting through the generalised Pareto distribution with covariates and so on, and that's what we did, and we applied this method and got some quite tight confidence intervals on the estimates, obviously subject to all the assumptions that the data was representative from the wave tank studies, and developed from a whole range of these, not just the ones shown here, which gave them a greater sense of what the probability of sinking was, and therefore what the scenarios that possibly led to that were involved. In terms of assessing fit, which is obviously critical to decide why our approach was better, if we look at just a QQ plot, you can see for distribution 1, the variable that it doesn't fit inside the tolerance intervals. When we look at the extreme points, it says in fact that it gives much greater fitted values than we might expect, which is why it overestimates the probability. Distribution 2, it fits okay in the upper tail, but fits very badly in the middle of the distribution. and whereas the generalized Pareto distribution fits beautifully all across the range of data, as we would have expected. So the judge in this case concluded that our evidence was vital to the investigation, and then authorised us to take subsequent work that would design new global standards for how strong these hatch covers should be for all types of major shipping. And that led eventually to an increased level of the design standard, and there's a lot of evidence to show that's really changed the safety of these similar type of ships. In terms of heat waves, that's the next topic I want to get into. So heat waves are much more subtle in the type of extreme events that we're looking at. Because a heat wave is a set of hot days. It isn't just a single hot day, it's a set of hot days which increase mortality. And we know that basically once the heat gets above somewhere like 35 to 37 degrees, then the bodies start to respond very strongly to that through a form of heat exhaustion, often leading on to death, particularly for people who are frail already or young. And the impact of the heat wave is really felt through a combination of the duration for an individual's, but of course for a population it's obviously determined by the spatial extent of the heat wave. So we're interested in now in looking at heat extremes, we're interested in the groupiness then of these hot days in terms of at an individual site, or the groupiness in space in terms of determining the spatial impact of the heat wave. We know from data in Europe that basically once it exceeds 35 degrees, then mortality goes up to by almost a factor of 50%. So anything above 35 degrees is important. And so the new thing that comes from the extreme value problem here is we've got to worry about the dependence between these big values either in space or time, and potentially to account also for some covariant factors which maybe change that relationship. So to do this, we need to just quickly introduce the concept of multivariate extremes, going back to the work of Vic. And so Vic's work, which I've looked at, as I say, talking about ordering, but basically the full joint distribution, if we look at that, we can write down in terms of its marginal distributions, which are joined together through a copula function, which contains all the information about the dependence, having effectively transformed the marginal variables to have common scale. Here it's set out as having uniform scale, but I'm going to do it working with Laplace scale variables just because that gives a nicer mathematical presentation. And the key thing that I want to do here is I'm going to model this joint distribution when at least one component of y is large. So if we think back to the univariate case, what was the philosophy? The philosophy was by focusing on the tails of the distribution, we can narrow down the class of possibilities of distributions that's sensible to look at. Here, obviously again an infinite set of copulas, it's just a joint distribution function, there's an infinite set of those. But by focusing on the copula, conditioning on the fact that one of the variables is large, what we're hoping to do is we'll find a nice mathematical simplicity to the types of copula form that can come out in that case, and that will lead us, just like in the univariate case, to a much simpler family that we can focus on and use with theoretical justification to extrapolate. So the strategy of what we're going to do here is we're going to model each of the marginal variables. As I say, because we're thinking about it in a copula scale, we're transforming them to have common marginal distribution, which in my case will be Laplace. The nice thing about it is it's got exponential upper tail. That gives me then a simpler form for the copula, as we just were mentioning, and the simpler form actually comes through for a particular model then that I'm going to use, which I developed in the past with Joan Hefner. And it comes at what I think is a particularly nice form. It comes expressed in terms of a conditional representation, which has a nice regression interpretation. Oops. So just diagrammatically, what are we doing? So here's our data after I put it onto common margins. I'm going to focus on looking at the variables when one of the variables is large. So in this case, let's just presume it's above the level 2. And then the idea is I'll develop a model then for the conditional relationship in this setting of y given x, which will then describe for me the joint behaviour up here. I can then simulate from my distribution. I know the marginal distribution, so that's easy. Simulate from the conditional distribution of y given x. do that repeatedly, and then I can work out through Monte Carlo methods the probability of any extreme set I'm interested in. Okay, so just quickly taking you through the stages of that, hopefully some of these will be apparent from what we set out before. So we saw before that from the univariate extremes methods that if we look at the excesses above some high threshold level, we can model those as a generalized Pareto distribution. So that's what we've got here. We've got a generalized Pareto tail, and because we're not worried about the middle of the distribution so much, I'm just going to estimate that using its empirical distribution function. Transfer to common margins, these Laplace margins through the probability integral transform, that's all it's doing there. And then I've got some new variables then, x1 and x2, which have got common marginal distributions. I mean, this is the top of the key complicated formula we've got to get through, and all I'm going to do is generalize this one more step after this. So in the bivariate case, this is what this approach comes down to. So I'm going to condition that I'm looking at one of the variables being larger. x1 is big. Then I'm going to look at the probability that x is bigger still. So look at the excess distribution of that, and it turns out that that is exponential. Well, because of the Laplace margins, that's automatic. That's just the lack of memory property or the no aging property of the exponential distribution. So that's not a surprise. The subtlety of this comes in this other component here. That conditioning on x1 being big, I'm going to be. It turns out that I can find an alpha and a beta such that this renormalization of x2 converges as u tends off to the upper end point of the distribution to a nicely non-degenerate limit. So the structure of the dependence between the extremes of x1 and x2 are all driven here by this parameters alpha and beta, with the subtlety of how that comes through the distribution g at the top of the normalized variable. So in particular, if I look at the case where alpha's 1 and beta's 0 in that setup, it just says x2 minus x1 in that situation. So it's really saying x1 and x2 are sort of growing at the same rate as each other, because as x1 gets large, if I just look simply at the difference between the two of them, that will converge nicely to a non-degenerate limit. And in fact, that's what I've basically got with data here, that if I just looked at the difference between x1 and in this case, y and x, once I'm looking at large values, that difference between those converges as I look to larger and larger variables. So, and in particular, a consequence of this is that there's a positive probability that I get my very biggest x2 occurring with the biggest x1 values. But whenever alpha's less than 1, basically x2 is growing at a slower rate than x1 once x1 is large. And so we can capture that sort of growth pattern there, and that occurs in sort of Gaussian variables and such like. And different values of alpha lead to different types of extreme dependence. Now, within the classic extreme values approach, pretty much everyone just works in this situation here, which restricts their ability to look at situations where the very biggest values increasingly less often occur together. And that's very important when we then look at the clustering of extreme values, as I'll point out later on. Same result applies in the vector version. Everything just stays exactly the same, just becomes vectorized here, so we now have a vector of coefficients of alphas and betas, but the subtlety is just sort of notation. It's the same idea. So how do we use this? Well, the way we use this result is just like we did with the generalized Pareto distribution. What we do is we assume that this limit result holds for a large enough threshold level. It holds exactly. And then we use that as our model. Just like going back to the central limit theorem, once we've got a large enough sample size, we believe the distribution of our sum is well approximated by the normal distribution. This is all that same type of asymptotic argument. So unravelling that then basically says that the rest of the elements of my vector, in my case of y, maybe on the earlier one of x2, is linked in a linear way to the other variable, and then in a parallel way to the first variable, times this independent variable that follows this non-degenerate limit. It looks very messy, but let's just unwrap that, because that's very messy. If we write it instead like this, it's basically saying that I've got a multiple regression, so a multivariate regression here. We've got a vector of variables linked to the first variable, which I know is large, in a linear way, and then also in a power way, where this mu is the mean of this distribution. And then I have an error variable with zero mean and unit variance here. So the variance of the conditional distribution grows in proportion to the variable I'm conditioning on in a power way. So we can just fit this model and estimate these alphas and betas just using standard regression type of methods with this particular mean variance relationship between the variables. So what we're doing, the critical thing we're doing here, as this picture shows, is we're fitting this regression relationship with sort of a mean growing and a variance changing over levels, but we apply this only in the extreme tail. So we're only fitting this above extreme levels for the variable we condition on. And then we do this for each of the variables. Okay, so let's run through some examples of how we've applied this. So let's look back to the 2003 European heat wave, which is almost as warm as in here, but not quite. So this caused 4,000 deaths. We're not going to get that today. It's got a huge loss to agriculture, and we've got data just to study this from one site in central France, where we've got data for a number of years, and in particular at that site, this critical level we were talking about earlier of the heat waves of 35 degrees is the 1 year return level. So it's the level which they expect to see once every year. But if we look at in the 2003 event, its peak was basically 40 degrees. Not typical Lancaster weather, is it, Peter? But close. So its peak was that, and the stunning thing about this event was not so much how hot that day was, but the fact that it was 11 consecutive days above the 1 year level. So you're getting this thing that you'd only usually expect once every year, you're getting it 11 times in the year and all following each other. And so that's what caused the deaths, was this persistence of this event. So what I want to do is just using this type of an approach, looking at the clustering processes we've just been describing, is to look at what's the chance of getting an event of that rarity. So the way we tackled this is by assuming a first order Markov model, but when we do higher order models, the results are very similar broadly. We then look at the lag1 dependence. We can then treat it as a bivariate problem. We estimate our alpha. You can see it's less than 1, so we're getting this asymptotic independence type situation I was describing earlier. And we can simulate from an extreme event and simulate forwards, and then there's similar type of parameters to allow us to simulate backwards. So this process turns out not to be time reversible in its extreme behaviour. It decays away faster, so slower after the peak than it rises up to the peak, so it rises up quickly to the peak in general. And then from this, we can find various different features. So we've got a model then for the joint process over large events. So we can see that the actual event itself, in terms of its peak, was a 1 in 50 year event. In terms of its clustering, we'd see on average, at the level we were looking at the 1 year level, we would only expect on average, once we got in a peak value above there, we'd only expect to see 2 days on average above that 1 year level, with quite a small confidence interval there. But the traditional extreme value models would have said that number stayed the same as we got to higher levels, whereas actually it turns out within the models that we're fitting, and looks much more so appropriate for these, is that as you get to higher and higher levels, that mean cluster size decreases. So generally the peaks are much more pointy, much more extreme, localized. And then if we look at what's the probability of getting an event that lasts above the 1 year level for 11 consecutive days, it's basically a 1 in 1,000 year event. So the thing that's particularly for this event that was extreme isn't particularly how hot it was at its peak, but it was the fact that it lasted so long. And obviously you can combine and put together these things to say, well, what's the chance of getting an event that exceeds that level and lasts so long as well. The other example to do with heat waves is looking at Australia. A heat wave that occurred there about 5 or 6 years ago didn't cause quite so many deaths, but it was particularly extreme in this area of Australia between Melbourne and Adelaide. So Melbourne got its record temperature in 150 years, Adelaide got its 3rd hottest temperature, and here we've got data on a spatial scale for this event in the form of gridded data, so not actual direct observations, but observations where they've been pulled together to give information over the grid. Now, in this context, in this problem, the key information that is really about how, and interested is how does the large-scale phenomena to do with the El Nino process, the El Nino sudden oscillation, how is that affecting the chances of getting such an extreme event? So we've studied that in this case, in particular using a particular index which describes how this varies. And typically what happens is that the El Nino is a process to do with the cooling and warming of the oceans, which then creates particular winds which will bring warm and cold weather towards Australia. And in particular the east coast of Australia, nearer where Melbourne is. And so what we're trying to do is we're then trying to put this covariate into our extreme value models, both in terms of the marginal parameters, but also the dependence parameters it's described in the clustering effect. So if we just look marginally, first of all, what the effect of El Nino is. So this is the 1 year level as estimated for Australia for the particular value of the El Nino signal in that year. And you can see that they have quite hot temperatures there relative to what we're used to over the country. And then you can see here it's just a map showing the difference between the typical El Nino in its upper cycle and lower cycle, and how that affects the 1 year level. And you can see that the biggest differences tend to be on the east coast, which is what we'd expect given the way that this process works. If we look at the chance of big values occurring together at different points in space, so conditioning on Melbourne being extreme, ask what's the probability that, so suppose Melbourne was above its 90-year level, what's the 90% quantile, what's the probability another site's above its 90% quantile? Just empirically, that's what we get. From our model, that's what we get, so we get a good agreement there. But critically, the bottom here is looking at, looking at the right-hand column is looking at what happens if we go to the 1 year level. So conditioning on Melbourne exceeding its 1 year level, what's the probability the other sites also exceed their 1 year level? And you can see that the event becomes much more localised once we look at these more extreme events. So if Melbourne's extreme, it's less likely that other places are going to be so extreme as Melbourne as we move further away in those cases. And again, if we'd used asymptotic, the classic extreme value models, we wouldn't have got that decaying or much more focused behaviour as we go to the more extreme events. So the model seems to capture the basic dependence quite well. But in terms of understanding about the event, the key measure is to look at the meteorologists have used the standard measure, which is to do with this severity area frequency, which basically picks out the worst 1 year level, so worst return level event at one point in the grid, and plots that against 1, and it takes this next second biggest return level event in terms of its return period, averages over the two of them and then plots that and so on. So it gradually builds out looking at the average of the worst J return periods for the event over the space. So it collapses this spatial event into sort of a measure of how severe things are around the most extreme point. And so this is a classic measure that they have. Now, if you just take it for all the data, ignoring the ENSO signal, the black line is the pattern through observed data. The blue is what we get under our model, which misses this, and the red is what happens if I'd assumed asymptotic dependence. And again, that's missing the bit of the truth. But actually, if we put the ENSO signal in here, recognising the state of where we were in the cycle of these, then it turns out that the black curve fits beautifully inside what we would predict then under our particular model. As we can see that we can capture that very nicely in terms of its spatial characteristics, but particularly tied in through this subtle behaviour of the ENSO signal, which is not at all picked up at all once we use this asymptotic dependence model. And so we can actually characterise these data, we can actually look at how rare this event was, as judged by what's the probability that we get a severity area value that's greater than, say, the observed value for this particular event. We can separate and work that probability out depending on the state of the El Nino signal. Now, in particular, for this year, 2009, although it was an extreme year in heat, it actually was an I can't say it, La Nina. Hugo, how do you say it?
La Nina.
Yeah, thank you. Those years, as opposed to an El Nino year. So, and the El Nino years are typically expected to be hotter, so the chances of the event if it had been a El Nino, would have been particularly, wouldn't have been particularly rare, maybe once in a 1,000-year event, but actually given it was occurring in a La Nina, it actually is a much rarer event, which is sort of very interesting. Peter, I've got 2 more minutes.
Sure.
I'll miss out my next example. It looks very pretty, which is a shame, but never mind. So let's just quickly summarise. I think what hopefully I've managed to convey is that the extreme value methods that we've been working on have a really strong, rigorous, probabilistic mathematical basis, which is important when we're looking at extrapolations because as we've been taught in all statistics, that we shouldn't extrapolate at all. So given we've got to do this, we need at least a framework that we sort of at least gives us a starting point to think about how to work in these cases. Now, the theory doesn't tell us everything, and this is a big feature that people who work in extreme value theory, I think all the time think that because we've got this theory, it means it must be true, but of course we're applying this in finite application cases where we don't know all the assumptions are true. So I would argue that these things are good starting models to describe what's going on, and we've got to respond and listen to the data very critically in those situations as well. Because we're working with extremes, we're focusing on the tails, we've always therefore as a consequence got limited data. And we've got to find out as much as we can and pull as much information in from other extreme value information that we can to do the inference efficiently, which is always really difficult to do. But a key part of doing that is to sort of build as much structure as you can in from the application area that you're working with, and in particular, sort of getting that physical knowledge from that domain, the domain specialists in there is really key. In all the examples I had, so knowing to work with the ENSO and exactly which particular form of that was critical in the Australia work. In the ship sinking, the fundamental to be able to solve that problem really was the construction of really very helpful covariates that link between the wave conditions and the wave impacts. The extreme value analysis is all very nice, but the covariates were fundamental to that. And then going back to the sea level extremes, the way that this was solved in a reliable way is to have that clear science of understanding about the subtleties of the interaction plane between the surge and the tide, and be able to tease that out in a way that was reliable then for extrapolation. So having that domain specialist knowledge mapped in is key to all of this. In fact, environmental statistics, it's not a statistician doing environmental work, it is really a collaborative effort, I think, in working on these. And I've been very fortunate to have worked with exceptional collaborators over time. So I've had a number of very, very good PhD students I've loved working with, but I've also had some external science domain experts which are fundamental to doing the work. And obviously I'd like to thank both the ones in sort of the traditional research centres, but also increasingly people I think who work in some of the more seen as industry partners have incredible strength in those areas and a lot of drive to solve real problems. So thanks.
Thank you, John. John's happy to take questions or comments. I have several, but I don't want to hog it. Go.
I can't help asking, given the length of your discussion, if you've tried to look at any trends that might be caused by things like
the fireworks people.
We're all really special, by the way.
Yeah. Sorry, so.
Oh, well, I was asking about global warming.
Yes, yeah.
And the extent to which you maybe tried to develop your models to take into account some kind of trend, greater variance.
Yes.
Temperature patterns.
Yes. So very nice example, say, is the work that we've been doing with Hugo on the heat waves, where you can use climate models to at least sort of try to get a sense of, as you get a certain level of changes to the mean of the process, what's the resulting change in the extremes and the characteristics of those. And nearly in all of those models, what you see is much greater response in the extremes than to the mean. So you get if you get a 1 degree increase in the mean temperature, what that's typically leading to is a 2 degree or 3 degree increase in the return, these high return levels, and also there's a risk that the clustering also changes. You can see for the heat wave in Europe, the critical thing was the clustering. So it isn't so much the individual heat. So a key part is in studying things like that is also studying how the dependence structure is changing with climate change, which I think is very rarely looked at. People tend to look at the marginal features, forget about the critical importance of the dependence structure. And so both of those events would have been much worse if their spatial or temporal extent had increased.
I mean, just a quick corollary to that, so it might turn on me slightly, might you observe a 1,000-year event in 2003, you observe another one 6 years later. That's kind of telling you something about climate change.
It is.
Yes.
It is. Yeah. These events aren't that rare, though, are they? So
No, they're not as rare as they used to be.
No, but not even that, though. But you can observe. If you think about a process that's reasonably close to being independent, it's not that unlikely to get a 1,000-year event over a big spatial scale.
Indeed. Yeah. Yes.
Coming back to the terminology, 100,000-year event, I think.
Yes.
And you say that, and people think, oh, in 1,000-year, what would be different, etc., and we have it next year. I find it always challenging communicating those kinds of extreme probabilities. And so I work in the insurance industry where people, when you say there's a 1 in 10 event and it happened this year, well, we should be fine for the next 9 years. So,
yeah. I mean,
it's a better approach to.
Well, I think clearly, whenever we talk about these things, we always talk. Actually, amongst ourselves, we talk about them as probabilities, but it just becomes easier to at least get a quick sense of scale. But it's all under the pseudo assumption of stationarity and all sorts of this.
Yeah.
So. They're not the easiest things, because obviously you can see the probabilities we're talking about there were very, very small. It's easier just to flip it into a return period statement. But yes, I think it's an unhelpful terminology that just lives on. And sorry, I've persisted with it today.
I was just wondering if you found it better.
No, I think just talking about the probabilities of these things is most clear. Yeah.
Just a slight. Sorry, you go first. I don't think the chair.
Am I right in? I could be. My memory may be failing. But am I right in thinking that the Derbyshire was actually found by Bayesian search methods?
No.
No, it's not. It's not one of the ones.
No, that was
something else.
That was the French aeroplane that was coming back from Brazil.
French Airbus.
Oh,
About the small coincidences. I was on exactly the same flight, exactly 1 week earlier.
You weren't on the Derbyshire as well.
No, I wasn't on the Derbyshire as well. So. See, it's only one coincidence. So it's a bit of an anarchy question, but when you started modelling one of the variables given all the others, you immediately think Markov random fields. Mm-hmm. Is there an issue with the self-consistency?
Yes. But it's quite subtle in the sense that actually once you're conditioning on, particularly when you're in this asymptotic independence case, because the two domains basically separate there, because once you're conditioning on one variable big and big, if the other one isn't actually that big at the same time, it never gets into that sort of joint tail region. But yes, when you get into that joint tail region, there are issues there, and we sort of impose some self-consistency in the fit, but it's very difficult to actually honour truthfully the asymptotics with the self-consistency, because the asymptotics are telling us about when these two distributions effectively have separated from the two different ways of conditioning, whereas you apply it at a finite threshold level where they haven't. And so you're trying to get the best of both worlds in there, but there's no easy solution to that.
It's a little bit like having your cake and eating it, isn't it? You invoke a regime in order to do what you need to do, within which the problem vanishes by that invocation. Please.
So extremalized statistics works and it's very nice, but in practice, I work on flood peaks and they don't use the GV, they don't use the generalized array, and I suspect it's the same in other applied fields. Any, so it's true that the GLO fits fair well for river peaks.
For example, one of the distributions. So in the flooding situation I'm familiar with there, what often happens is that the GV doesn't fit well at all. And part of the reason for that is you actually get clustering of of events. So you get certain years with far more events than you'd expect as a Poisson process. But if you actually then model that process as having, with the over-dispersion aspects of the Poisson on top of the Poisson process, and still modelling them basically as GPD, then you get through some of these things like the generalised logistic distributions and things like that, which come through and people often use and find work very well in those contexts. So as I was trying to hint at with the second last slide, it really gives us a starting point, and in certain contexts we need to look much more carefully about how we adapt and build from that. But I do think the GPD still in many cases with rainfall does a very good job, but yes, it requires much more care in its application, and you can't just say, okay, you've got this off-the-shelf method, and I'm going to try it.
Any more questions and comments? I just got one last one. You present a compelling case for thinking about extreme value problems as extreme value problems. Mm-hmm. And I mean, another sort of thing that might convince the skeptics is showing that if you did have a particular parametric family throughout the distribution, you still wouldn't be losing much in the way of efficiency. Are there any results like that? It's, for example, it's one of the arguments that Cox proportion has a subpopulation.
I think if you did really value the distribution, you must be losing an awful lot of efficiency. But what you'd hope is that the methods that you use, say for threshold selection, would be telling you in those situations that you can pull that threshold level down to effectively use all the information.
Because the further down you pull it, the smaller the efficiency loss. But there aren't any general results.
No, because I think it all hinges on that level of second order, third order approximation you've got to make to say when you can cut off the extreme components from the non-extreme. Good question.
Can I just ask a quick one? Just thinking about the rainfall, and when I've looked at it, particular types of rainfall, you'll end up with problems with the shape parameter sometimes, where you don't have enough data, and the shape parameter gives you something really unbounded and you get crazy non-physical. And then I was thinking, well, if you had actually looked at rainfall, a lot of models across the world in different circumstances, would you maybe come to a conclusion that really there's a shape parameter that works for rainfall, and that you could constrain your GPD to be a particular shape parameter or within a range?
Yeah, well, it would be nice to think that, wouldn't it? So, I think that's what things like regional frequency analyses try to do, is by pooling information from neighbouring sites or from places which have got the same type of characteristics together, and identifying that the shape parameter has reasonably similar values over different sites. Whether you can, that means you can then at the end of the day quite treat it as if it's known, but certainly you can treat it as much more. You can pull information about that parameter to tie it down an awful lot more. Whether you put that in as a prior, very strong prior, or something like that might be a way of doing that. Certainly, though, as we move from application to application area, it is stunning how the shape parameter has certain values. Basically, you seem to reoccur in different contexts from situation to situation. So, deep down, almost do believe that there is probably some shape parameter there that you could almost pull information to get it to a much more clear.
Any more? Well, I mean, echoing John's last point, I mean, I think amongst many virtues, I mean, that beautiful survey really reinforces the mutually beneficial interaction between statistical method and scientific method. And I'm very grateful personally to John for giving us such a superb start to the Barnett series. You are all very welcome to join us downstairs for a drink. Just follow the narrow winding staircase and you'll find glasses of wine and soft drinks waiting for pleasure. We'll also put the fireworks on specially. But before we go downstairs, please join me in thanking John once again.